Hi, I'm Nayana Thankachan, second year MC student of Marian College Kuttikkanam. In this presentation, we are looking into multi-layer neural network. Before going to this presentation, we can see what all are the contents in this presentation. First, there is an introductory part, then what is multi-layer neural network, and rest of all topics comes under multi-layer neural network. That is history, architecture, and what is multi-layer Preceptons, multi-layer network for XOR, what is attribution function, forward propagation, feed-forward operations and classification in forward propagation, backpropagation, minimization of error using backpropagation stages, architecture, then training processes, algorithm and solution, factors affecting backpropagation multi-layer neural network, example with a solution, training protocol, backpropagation feature mapping, limitations, applications, and conclusion. Now we can look into our presentation. In the introductory part, we are discussing what is an artificial neural network and why the multiple layer or multiple nodes can be implemented in the artificial neural network. An artificial neural network is a computational model that is inspired by the way biological neural network in the human brain process information. That is, we are implementing neural networks in the computer artificially as same as the human neural network. That is an artificial neural network. Artificial neural networks have generated a lot of excitement in machine learning, research and industry, result in speech recognition, computer vision and text processing. Then what is the multi-layer neural network? This multi-layer network solves the classification problem for nonlinear sets by employing hidden layers whose neurons are not directly connected to the output. Why do we have multiple layer and multiple node per layer in a neural network? We need at least one hidden layer with nonlinear activation to be able to learn nonlinear functions. Basically, by adding more hidden layers or more neurons per layer, we can add more parameters to the model. Now look into multi-layer neural network. As mentioned in the introductory part, the multi-layer neural network solves the classification problem for nonlinear sets by employing hidden layers whose neurons are not directly connected to the output. The additional hidden layers can be interpreted geometrically as additional hyperplanes which enhance the separation capacity of network. We can see the history of multi-layer neural network. Deep learning deals with the training multi-layer artificial neural networks, also called deep neural networks. After Rosenblatt, Precepton was developed in 1956. There was a lack of interest in neural network until 1986, when Dr. Hinton and his colleagues developed the backpropagation algorithm to train a multi-layer neural network. Today, it is a hot topic with many leading firms like Google, Facebook, and Microsoft, which invest heavily in application using multi-layer neural networks. This is an architecture of multi-layer neural network. Here, there is two pictures. One is two-layer network and other is three-layer network. In the two-layer network, the inputs are come through input layers. I is getting in the hidden layer, and we can get the output through output layer. Now we are looking into the second picture, three-layer network. The inputs are come through input layers, and the activation functions and works in hidden layers. There's a specialty for the hidden layers. There's two type of hidden layers, hidden layer 1 and hidden layer 2, and the output we are getting through output layer. In the first layer network, we are getting multiple outputs with a single layer, single hidden layer. But in the second layer means second picture, three-layer network. There's two hidden layers and there's only one output layer. The detailed explanation of the above picture, the training occurs in a supervised step. The basic idea is to present the input vector to the network, calculate in the forward direction the output of each layer and the final output of the network. For the output layer, the desired values are known and therefore the weights can be adjusted as for a single layer network. In the case of backpropagation algorithm, according to the gradient descent rule. Artificial neural network has three layers, that is the input layer, hidden layer and output layer that we are already seen. Each artificial neural network has a single input and output but may also have none or one or many hidden layers. The structure of artificial neural network classifies into many types of architecture such as single layer, multi-layer, feed-forward, and recurrent networks. There are weights associated with each input neuron in artificial neural network, bias which also carries weight. In the hidden layer, the inputs come with the weights, the user-assigned weights. The activation functions are of many types such as binary step function, bipolar step, sigmoid function. Multi-layer Precepton. A Precepton network with one or more hidden layers is called multi-layer Precepton network. A multi-Precepton network is also a feed-forward network. It consists of a single input layer, one or more hidden layers, and a single output layer. Three layers in multi-layer Precepton are inner layer, hidden layer, and outer layer. In the inner layer, the input layer has three nodes. The bias node has a value of 1. The other two nodes take x1 and x2 as external inputs, which are numerically values depend upon the input dataset. As discussed above, no computation is performed in the input layer. So the outputs from nodes in the input layer are 1, x1 and x2 respectively, which are fed into the hidden layer. In the hidden layer also has the three nodes with the bias node having the output of layer 1, x1 and x2 as well as the weight associated with the connection or edges. The calculation for one of the hidden layers or hidden nodes, similarly the output from other hidden nodes can be calculated through activation functions. These are outputs and then fed into the nodes in the output layer. The output layer have two nodes which take inputs from the hidden layer and perform similar computation as highlighted above. The values calculated y1 and y2 are result of these computations act as output of the multi-layer Preceptons. This is an example of multi-layer network for XOR. Two connections in first layer not shown. There is a weight mentioned as 0. Then inputs value and the values comes to the hidden layer. The weight is assigned as 1, and we got the output rate. What is an activation function? The input layer takes a two-dimensional vectors as input. The output of each input unit equals the corresponding components in the vector. Each unit of the hidden layer computes the weighted sum of its input in order to form a scalar net activation. This is the inner product of the inputs with the weighted at the hidden layer. But lambda I index unit in the input layer, lambda j index unit in the hidden layer, and lambda wij denotes the input to hidden layer weights at the hidden unit j. The activation function represents the non-linearity of a unit. The activation function is sometimes referred to as a sigmoid function, a squashing function, since its primary purpose is to limit the output of the neutron to some reasonable range, like a range of -1 to +1, and thereby inject some degree of nonlinearity into the network. Each output unit similarly computes its net activation based on the hidden unit signals as where lambda k indexes unity in the output layer, lambda nh denotes the number of hidden layer units. Equation 4 is basically the same as equation 1. Thus here equation 1 can be taken as values in the input layer, and equation 4 can be depicted as the values in the output layer. Now we can see what is forward propagation. In the forward propagation, we can see feed-forward operations and classification. The class of solutions that can be obtained from networks that implement linear discriminant functions is not general enough in demanding applications. There are many problems for which linear discriminants are insufficient for minimum error. Multilayer neural networks learn the nonlinearity at the same time as a linear discriminant. They implement linear discriminant in a space where the inputs have been mapped non-linearly. They admit simple algorithms where the form of nonlinearity can be learned from the training data. This is an example picture of a feed-forward operation and classification. There is a bias as an input, and there is an output layer. Then is hidden layer. The bias and the weightage can be represented in this picture, and the input can be represented as I, hidden layer is represented as J, and the output layer is represented as K. As mentioned earlier, Wikj can be represented as the output, and Wij can be represented as a hidden layer, and the x1, x2 as an input layer. Each hidden unit computes a weighted sum of its input to form its scalar net activation, which is denoted simply as net. That is, the net activation is the inner product of the input with the weights and the hidden unit. Thus, it can be written as net j is equal to summation of I to 1d xi wji plus w0. This w can be represented as the weight of the inputs. And this is equal to summation of I to 0 d xi wji is equal to w of j g of x, where the subscript I indexes unity in the input layer, j in the hidden layer, wji denotes the input to hidden layer weights at the hidden unit j. Each hidden unit emits an output that is nonlinear function its activations f of net, that is yj is equal to f of net j. Above a figure shows the simple threshold of a sine signum function. F of net is equal to sine of net, that is 1 if net greater than or equal to 0, or minus 1 if net less than 0. But other functions have more desirable properties and are hence more commonly used. This f of dot is called activation functions or nonlinearity of a unit. Each output unit computes its net activation based on the hidden unit signals as net k is equal to summation of j to 1 n by j wkj plus w of k0 is equal to summation of j to 0 n by j wkj is equal to w of k raised to t y. And here in above equations, w of jx, that is an input layer equation, and w of ky, that's an output layer equation. But the subscript k indexes units in the output layer and nh denotes the number of hidden units. We have mathematically treated the bias units as equivalent to one of the hidden units whose output is always 0. Y0 is equal to 1. In this example, there is only one input. For classification, we will have the C output units. one for each of these categories, and the signal from each output unit is the discriminant function jk of x. We gather the results from equation 10 of to express such discriminant functions as jk of x is equal to zk is equal to f summation j to 1 n wkj f of summation j to 1 d wjik jixi plus w of j0 plus wk0. Here, the equation 10.1, 10.2, 10.4 and 10.5 depicts that the all equations above. The first equation is 10.1 and second equation is 10.2 and third is 10.4 and last one is 10.5. This is a picturization of above equation, or this is a graph of above equation. We can even allow the activation functions in the output layer to be different from the activation functions in the hidden layer, or indeed have different activation functions for each individual units. Now we can look into what is backpropagation. A backpropagation network is an application of feed-forward and multi-layer Precepton network with each layer having differentiable activation functions. For a given training set, the weights of the layer in backpropagation network are adjusted by the activation function to classify the input patterns. The weight update in backpropagation network takes place in the same way in which the gradient descent method is applied to the single Precepton network. The next topic is a minimization of error using backpropagation algorithm. In this algorithm, the error between the actual output and target is propagated back to the hidden unit. For minimizing the error, the weights are updated. To update the weights, the error is calculated at the output layer. For further minimization of error and to calculate the error at the hidden layer, some advanced techniques that will help in calculation and reduction of error at the hidden layer leading to more accurate output are applied. With a greater number of hidden layers, the network becomes more complex and slower, but it is more beneficial. The system can be trained with one hidden layer as well. Once trained, it will start producing the output rapidly. Now we can see the stages that included in the backpropagation. First is the input training pattern is feed forward, and second one is an error between the actual output and the target value are calculated. Then third one is a weightage update. Input layer, as we seen earlier, the input layers can be represented L1 and L2. The hidden layers with the weightage, the input layers with the weightage has come to the hidden layer, that is H1, H2, and there is an additional bias of B1, and the output layer O1 and O2, then additional bias B2. The input layer gives inputs as the with the weightage W1, W2, W3 and W4, and the activation functions as performed in the hidden layer, and the net result can go to the output layer with the weightage W5, W6, W7 and W8. The next topic is architecture of the backpropagation network. A backpropagation network is a feed-forward multi-layer network. It has an input layer, a hidden layer, and an output layer. The biases are added to the network at the hidden layer and the output layer with the activation function equal to 1. The inputs and outputs to the BPN can either be binary, 0, 1 or bipolar, -1 or +1. The activation function is a differentiable, monotonic, and incremental and is generally chosen between binary sigmoidal or bipolar sigmoidal. A backpropagation network has a feed-forward phase where the data is fed from the input towards the output, and the backpropagation space where the signals are sent back in a reverse direction to the minimize error. This is an architecture of backpropagation network. There's an input layer with a lot of inputs, and there's a one or two hidden layers with weightage, and this is represented as Z1, Z2 and up to Zp, and there's an output with a Y1, Yk and Ym. Training process of backpropagation algorithm. These are training propagation. First step is the initialize random beats and learning rate. Second step, the input unit receives xi as the input and sends it to the hidden unit. Step 3, the net input of the hidden layer and Zj is calculated as a Zoj plus summation of xi into Vij. Step 4, net output of the hidden layer is calculated as Zj is equal to f of Z input. The activation function is taken as binary or bipolar sigmoidal. Step 5, the net input of the output layer is calculated as Zj is equal to f of Z input. Step 6, the net output of the output layer f of y input. The activation function is taken as binary or bipolar sigmoidal. Step 7, calculation of where output units yk as k is equal to 1 to m receive the target pattern corresponding to the input training pattern, and we can find out the derivative of the function. Step 8, error correction and weightage adaptation. Weight adaptation can be implemented as the error of delta E is equal to tk minus yk into derivative of output layer f of y input wjk equal to alpha into delta E into Zj for kth neuron. For bias, delta W0k is equal to alpha into delta E. The error is sent backward. Step 9, the output units are updated. Yk, there is a k is equal to 1 to m updates the bias and weights. Now we are updating the updated the kth neuron and bias. We are calculating the weight of kth neuron and calculating the weight of bias. Wjk new equal to Wjk odd plus delta of Wjk. W0k new is equal to W0k odd of delta W0 of k. Step 5, check for the stopping conditions that is given as a number of epoch completed. Step 2 to 9 are repeated until the stopping condition is obtained. Now we can see the factors affecting the backpropagation network in multi-layer neural network. Initial weights, learning rate, number of training data, number of hidden layers, nodes. The initial weight is the random weights chosen of very small value as the larger inputs in binary sigmoidal functions may lead to the saturation at the very beginning, thereby leading the functions being stuck at local minima. Learning rate, a large value of learning rate helps in faster convergence but might lead into overshooting. The range of from 10 to 3 to 10 is used for various backpropagation experiments. 10 raised to 3 to 10. It is a range can be used in the learning rate. Number of training data. The input training data should cover the entire input space and the set of input sets should be chosen randomly. Number of hidden layer nodes. The number of hidden layer nodes is chosen for optimum performance of the network. For networks that do not converge to a solution, more hidden nodes can be chosen, while for network with fast convergence, few hidden layer nodes are selected. Example of backpropagation network with the multi-layer neural network. For the following network diagram, let's calculate the new weights with the given figure. This is an example with the input vector 0, 1, target output 1, learning rate is 0.25. Activation function is called a binary sigmoidal activation function. And the solution is, from the above diagram we can see the input vector to Z1 that is V11, V21, V01 is 0.6 minus 0.103. Input vector to Z2 is V12, V22, V02, that is minus 0.3, 0.3 and 0.5. Here we can see that all weights in this figure. And the input vector to Y, W1, W2, W0 is 0.4, then 0.1 and minus 0.2. The activation function is given by f of x is equal to 1 by 1 plus e of minus x. The input x is equal to 0, 1 and target t is equal to 1. And we can calculate as a step by step. Step 1, calculate the net input weight of Z1, that is Z in 1 is equal to V01 plus Z1 into V11 plus x2 into V21. That is 0.3 plus 0 into 0.6 plus 1 into 1.1. 0.1 is equal to 0.2. Now we can calculate Z into is equal to V02 plus x1 into V21 plus x2 into V22. That is 0.5 plus 2, 0 into 0.6 plus 1 into 0.4, that is 0.9. Step 2, apply the activation function. Zi is equal to f of z in 1 equal to 1 by 1 plus z raised to minus x in 1. That is 1 by 1 plus e raised to c minus 0.2, that is 0.5498. Zj is equal to f of z in 2, that is equal to 1 by 1 plus e raised to minus x in 2, that is 1 by 1 plus e raised to minus 0.9, that is 0.7109. Step 3, calculate the net input of output layer. That is y in is equal to w0 plus zi into w1 plus zj into w2, that is minus 0.2 plus 0.5498 into 0.48 plus 0.7109 into 0.1. That is the value 0.549 is obtained from zi and 0.7109 obtained from zj, and its total value is 0.09101. The step 4 is equal to calculate the net input using activation. That is y is equal to f of y in is equal to 1 by 1 plus e raised to minus y in 1 by 1 plus e raised to minus 0.09101, that is calculated in the step 3, and the answer obtained in step 4 is 0.5227. And step 5 is a calculation of error. Delta E is equal to Tk minus Yk into derivative of f by y in. Derivative of f of y in is equal to f of y in into 1 minus f of y in, that is equal to 0.522 into 0 into 1 minus 0.5227, that is 0.2496. Delta E is equal to Tk minus Yk into derivative of Fy in, that is 1 minus 0.5227 into 0.2495 is equal to 0.1191. Now we can update our weights, that is step 6, weight updation. Delta W1 is equal to alpha into delta E into Z1, that is 0.25 into 0.1191 into 0.5498, that is equal to 0.014. And delta W2, weightage of second weight, is equal to alpha into delta E into Z1, that is equal to 0.25 into 0.119 into 0.7109, that is equal to 0.02117. Step 7 is a new weightage calculation. W1 of new is equal to W1 odd plus W1. 0.4 plus 0.0164 is equal to 0.4164. W2 new is equal to W2 odd plus W. Delta of W2 that is equal to 0.1 plus 0.02117, that is equal to 0.12117. Thus, the final weights are calculated as the W1 nu is equal to 0.4164 and W2 nu is equal to 0.12117. Assumption: the error between the input and the hidden layer vectors is taken as 0. The next topic is backpropagation analysis. But if we set the all initial weights Wkj to 0 in the update rule, clearly delta of Wji, that is our weightage from input layer to hidden layer, is equal to 0 and the weightage would never change. It would be bad for all network weights were ever equal to 0. This is why we start the network with random weights. The update rules discussed only apply to a 3-layer network where all of the connections were between a layer and its preceding layer. The concept can be generalized to apply to a network with n hidden layers to include bias unit to handle a different layer range for each unit, etc. It's more difficult to apply these concepts to recurrent network where there are connections from higher layer back to lower layers. There are some training protocols. Training consists of presenting to the network the collection of pattern whose category we know, collectively known as a training set. Then we go about finding the output of the network and adjusting the weight to make the next output more like the desired target values. The 3 most useful training protocols are stochastic, one-line, batch. In stochastic and batch training method, we will usually make several passes through the training data. For online training, we will use each pattern once and only once. We use the term approach to describe the overall number of the training set passes. The number of approach is an indication of the relative amount of load. In stochastic training, we have an algorithm. In stochastic training, patterns are chosen at random from the training set and networks are updated from each pattern presentation. Stochastic backpropagation algorithm. There's a 7 step. First step, we begin initializations. Initialize NHW criterion 0, theta, n, and m to 0. Second step, do m to m plus 1. Visualizing that m is a 0 in the beginning, and in the second step, we do m is equal to m plus 1. We are incrementing the m. Third step, xm is equal to randomly chosen pattern. Fourth step, wij equal to wji plus n of delta j xi wkj of wkj plus n of delta k by I. Repeat the step until delta jw less than or equal to theta. And in this step 6, return the value of weight, that is w, and in the 7th step 8. Online training, each pattern is present once and only once. There is no use of memory for storing the pattern. Useful for live training with human tester. It is an algorithm same as the stochastic training with some several step difference. Next is a batch training. In batch training, the entire training set is presented first and their corresponding weights updated as summed. From there are actual weights in the network are updated. This process is iterated until the stopping criteria is met. The total training error over an individual pattern can be written as summation of p to 1n j of p. This is an algorithm for batch backpropagation. Is the same as stochastic and online with some step differences. Backpropagation as feature mapping. Hidden neurons play a critical role in the propagation of a multi-layered network with backpropagation learning because they act as a features dictators. As the learning process progresses, the hidden neuron begins to gradually discover the considerable features that characterize the training data. They do so by performing a nonlinear transformations on the input data into a new space called a hidden space or feature space. In this new space, the classes of interest in a pattern classification task may be more easily separated from each layer than in the original input space. This is a picture depicting in the backpropagation feature mapping with the input representations and the hidden representations. And in the hidden representation, the fader decision boundary can be found from the graph. The above shows a three-layer net addressing the XOR problem for any input pattern in the x1, x2 space. We can show the corresponding output of the two hidden units in the y1, y2 space. The small initial weights, the net activation of each hidden unit is small, and thus a linear portion of this activation function is used. Such a linear transformation from x to y leaves the patterns linearly inseparable. And the next topic is the limitations of multi-layer neural network. There is some limitations in multi-layer neural network. Usually, the problem given to the neural network is described as a set of examples rather than a function. Therefore, the number of points in the problem space is finite. Neural networks which are trained properly have a good interpolation performance but a very poor exploration performance. Unfortunately, there is no general rule to find out if a new pattern is within the interpolation space. To define a measure for a generalization ability is very difficult. A good generalization always depends on the data set, but is for one application might be desirable is useless for another. Multi-layer neural network trained the backpropagation depend on the correlation between input and output variables. They show that backpropagation's multi-layer Preceptons have a very poor generalization ability for statistically neural problems. Statistically neutral in this context means that no knowledge of the expected output value can be drawn from the knowledge of a single input variable. Only the relation between different variables determine the output. Using a sparse coding of the problem to supply the backpropagation with the correlated input variables ensured that this approach can improve the generalization ability of backpropagation training artificial neural network for statically neural problems. Sometimes the real-world problems are really taught as statistically multi-layer neural network. This is some applications of multi-layer neural network, type of feed-forward neural network applications and brain modeling, but needs modeling. That's the brain modeling. It includes development, adult performance, neuropsychology, analysis of hidden unit representations. Third one is a real-world applications data compressions. It is PCA time series prediction character recognition and what were autonomous driving. That is ALV. Now there's a conclusory part. In the conclusion, we are we are getting into an assumption that we need at least one hidden layer with a nonlinear activation to be able to learn nonlinear functions. Basically, by adding more hidden layers or more neurons per layer, you add more parameters to the model. Neural network is a vast subject. Many data scientists focus only on neural network techniques. In these sessions, we practice the introductory concepts only. Neural networks has much more advanced techniques. There are many algorithms other than backpropagation. And the neural network particularly work well on some particular class of problems like image recognition. The neural network algorithms are very calculation intensive. They require highly efficient computing machines. We need to try different types of options and packages. Currently, there is a lot of exciting research going on around neural networks. and some of references. And that's all about multi-layer neural network. Hope you are all understand this. Thank you.